Welcome to this NPTEL online certification course of analog electronic circuits. Myself Pradeep Mandal from ENEC department of IIT Kharagpur. We are continuing this course for quite some time, and today's topic of discussion it is common base, common gate amplifiers. In fact, this is continuation of our previous lecture. So, we already have discussed about the theoretical aspect. Today, we will go with more numerical examples. So, our plan is to cover the following items of this topic. As I said that we already have discussed about the motivation of going for this common base and common gate configuration. We also have discussed about the basic operation and biasing of these two configurations, and also we have talked about small signal analysis for different performance parameters, namely voltage gain, input impedance, output impedance and current gain. Today, we will be covering number of numerical examples associated with these two basic configurations, and whatever the expression we have obtained in the previous class of different parameters, that will be extensively used here, and we will get numerical value of those parameters. And subsequently, once we cover these numerical examples which are associated with analysis of a designed circuit, once we are comfortable on these numerical examples, then we will be in a position to discuss about what may be the design guidelines for a given requirement of the circuit performance. So, today's discussion here it is number of numerical examples and then design guidelines of common base and common gate amplifiers. So, let us go to the numerical example of common base amplifier. What we do have here it is the basic circuit given here, and you can see that we do have ideal bias as well as more practical bias of the collector terminal, and also at the base node of this circuit we do have a DC voltage along with Thevenin equivalent resistance of the DC source. And since it is common base configuration and we want this base node should be AC ground, to ensure that we are also connecting CB large capacitor there. Input port is at the emitter and output port is at the collector terminal. Input we are giving through a DC decoupling capacitor. In this case, in this example, we are showing input signal in the form of voltage, and the signal source it is also having its source resistance called RS. And here we do have different parameter values, namely VBE on of the BJT it is approximately 0.6, current gain beta of the transistor it is 100, early voltage of the BJT it is taken 50 volt, and then base to emitter small signal capacitance C pi it is 10 picofarad, and on the other hand base to collector capacitor C mu it is having a value of 5 picofarad. These are typical numbers, and then also we do have the information about the supply voltage 10 volt, and then base voltage DC voltage 6 volt, thermal equivalent voltage VT it is 26 millivolt, and then also we do have the load capacitance connected at the output node which is 100 picofarad. Now, in this bias circuit we do have I bias which is given as 1 milliampere. So, for the time being in this numerical example, so we are considering this emitter bias, it is ideal. So, we do not have any associated conductance of this bias circuit. In later examples, we will be replacing this ideal bias by resistive bias. And in this numerical example, let we consider that the source resistance R s is equal to 0 and also the Thevenin equivalent resistance for the base bias R b, let we consider this is very small. So, whether we do have C b or not, we can consider that base terminal is AC ground. At the collector terminal, on the other hand, we do have practical circuit R c, and let you consider its value, it is 3 kilo ohm. So, how do we find different performance matrices of this circuit, which are enlisted here, namely voltage gain, input impedance, output impedance, input capacitance, maybe upper cutoff frequency of the amplifier, while we are driving the signal in the form of voltage. So, how do we proceed? We can start with the operating point of the transistor. To get the operating point of the transistor, we can do the DC analysis, and then we will be going to the calculation of small signal parameter of the transistors, namely GM and then R naught of the transistor. So, let you target at this point and try to find the operating point of the transistor. So, as I said, let us try to find the operating point. If you see that this I b, it is given as 1 milliampere and beta is 100. So, we may approximate that collector current I c is equal to I e, and which is same as 1 milliampere. So, this is the DC current, and then the voltage at the base, it is given as 6 volt, and the emitter voltage here, it can be obtained by considering 6 volt here and VBE on of 0.6 volt. So, we can say at the emitter node we do have 6 minus 0.6, that is 5.4 volt. Now, if we have this 1 milliampere of current at the emitter, approximately the collector current is also set by that, then the drop across this R c, it's 3 k multiplied by 1 milliampere. So, that gives us this voltage, it is V R c equals to 3 volt. VDD on the other hand, it is 10 volt. So, the voltage coming at the DC voltage coming at the collector terminal, it is 10 minus 3. So, that is 7 volt. So, if you have 7 volt here at the collector and at the base we do have 6 volt, the transistor it is in active region of operation. In fact, to consider this approximation, it is very important to ensure that the transistor it is in active region of operation. So, that is how we obtain I c. So, now the operating point it is we obtained. In fact, we can find what is the corresponding VCE voltage, which is 7 minus 5.4 here. So, anyway, then we come to the calculation of small signal parameters. So, let we consider small signal parameter calculation, namely GM of the transistor, which is I c divided by thermal equivalent voltage V t, and it is given 26 millivolt. So, we can see this is 1 by 26 mho, and then the other parameter it is R naught, and its expression is early voltage V A divided by I C, and early voltage it is given here, it is 50 volt, and I C it is 1 milliampere. So, that gives us R naught equals to 50 kilo ohms, and then R pi, which it can be obtained by considering this G m and the value of the beta given here. So, this is beta divided by G m, can say this is 100 multiplied by 26. So, that gives us 2.6 kilo ohm. So, these are the small signal parameters we obtain. Now, using those parameters, we can find the corresponding voltage gain. So, let us see how we do get the voltage gain. So, the voltage gain starting from the emitter terminal to the collector terminal, and if I call that voltage gain it is A V, you may recall from our previous day's discussion, it was G m into R naught plus 1 divided by R C plus R naught into R C. In fact, if you compare G m into R naught and 1, definitely we can approximate this by G m into R naught only. So, we can drop this 1 and we can say that this is G m into R naught into R C divided by R C plus R naught, which is actually R naught and R C in parallel. So, the voltage gain, now if I plug in this value of this G m and then R naught and then R C of 3 k, what we will get here, it is 1 by 26 multiplied by R C, it is 50 k into 3 k divided by 53. So, this is k and this is 1 by 26. So, I should say this is multiplied by 1000. That gives us a gain of say, so this resistance, if you see this resistance, let me write that part also separately. So, G m it is 1 by 26 and this part it is 2.83 kilo ohms. In my previous calculation, I already have done this one. So, that gives us the gain, which is equal to 100, roughly 100 to be more precise, 108.85. So, that gives us a very decent gain of this circuit. In fact, this gain it is very close to the gain of common emitter amplifier having the similar kind of bias level. So, that is how we obtain the voltage gain. Note that in this example, we are considering that R s is equal to 0. So, whatever the input voltage you are applying here, even though this circuit is having very low input resistance, since this R s we are considering it is very small. So, we can say that almost entire signal it is reaching to the emitter, assuming of course, this capacitor it is successfully allowing the signal to be coming to the emitter. So, this gain it is the not only emitter to collector gain, but it is also representing primary input to the primary output gain. Now, next thing is the input impedance. So, let us look into the input impedance. Let me use different color for that. Hopefully, I will be able to manage to write that expression here. R in, again you may utilize the previous derivation. So, if I look into the emitter terminal, what we have here, it is R pi, that is the resistance from emitter to base, and the base node it is AC ground. So, that is coming in parallel with whatever the impedance we do have out of this entire circuit. Let me use different color. Yes. So, we do have input resistance looking into the emitter. The input resistance, it is expected to be R C plus R O divided by G M into R O plus 1. So, I should say that this is again G M into R O, it is dominating, and not only that, if you see the value of this R naught, which is 50 K, and then this R C it is only 3 K. So, we can approximate this by R pi in parallel with 1 by G M. And again if I compare the value of this R pi and 1 by G M, they are having a ratio of beta. So, further to that, we can simplify or approximate the input resistance by 1 by G M 1. So, the summary is that the input resistance of this circuit, it is 1 by G M, and that is 26 ohm. So, naturally this input resistance is quite low. So, this input resistance as expected, it is quite low, 26 ohms. In fact, if you consider this R pi and R C also here, it may be slightly different, but more or less its value, it is quite low as 26 or 25 ohm. Now, next thing is that we can try to find the output impedance. So, I think the board is really clumsy. So, let me erase, but you please make a note that G M it is 1 by 26, R O equals to 25 kilo ohms, R pi it is 2.6 kilo ohm. Okay. So, we need to calculate the output impedance, and as I said that G M is equal to 1 by 26 mho, R O equals to 50 kilo ohm, and R pi is equal to 2.6 kilo ohm. Now, looking at the at this point, if I want to know what will be the corresponding output resistance. So, that output resistance, it is resistance of this R C, this path, and then the other resistance coming from the active device in parallel. So, that is in parallel with whatever the impedance we will be seeing. Now, if I consider R S equals to 0, as we have discussed earlier. So, this emitter node, it is getting grounded, and the impedance we will be seeing here, it is only R O. So, the net output resistance, it is R C coming in parallel with R O. Now, R C it is 3 K, and R O it is 50 kilo ohms. So, earlier we already have calculated this resistance while we are calculating the voltage gain, and that is 2.83 kilo ohm. So, that is the output resistance. Now, next thing is the input capacitance. So, if you see the capacitance at this node for the signal, of course, this signal coupling capacitor, it is quite large. So, whenever we are talking about input capacitance, it is coming the emitter to whatever the ground node, AC ground node will be considering, that is the net capacitance. Now, emitter to base, we do have C pi, and then also base to collector we do have C mu coming out of the device. So, if you look into emitter, and since the base node it is AC ground, whatever the input capacitance we will see here, it is only C pi. In fact, to be more precise, if I consider this is our primary input, and if I call that this coupling capacitor, signal coupling capacitor, it is C1. So, then the input capacitance, strictly speaking, it should be C1 in series with this R C pi, and whenever two capacitors in series, their value it is C1 C pi C1 plus C pi. Now, this C1 it is typically much higher than C pi. As a result, you can say that since this is much higher than C pi, so you can approximate this by C pi. So, that gives us the input capacitance. Now, next thing is the upper cutoff frequency of this circuit, and since we are dealing with the signal in the form of voltage. So, the upper cutoff frequency, of course, it is coming from the output resistance here and the corresponding CL here. So, omega upper cutoff frequency, it is 1 by R out into CL. So, you can find what may be the value of this one. CL it is given here, it is 100 picofarad, and R out we already have calculated 2.83 kilo ohms. So, we can find the corresponding value here. So, that is how whenever we do have the common base amplifier circuit, we can analyze the circuit, and as I said that end of this analysis what we obtained, that the voltage gain it was very good, 108.8. Input impedance it is low, 26 ohms. Output impedance it is decent, it is 2.83 kilo ohms, and input capacitance on the other hand it is low. So, I should say it is 10 picofarad only, and C mu it is not having any effect on C in. In fact, that is a good sign. If you compare this common base and common emitter amplifier, and if you recall for common emitter amplifiers input capacitance, it was C pi plus Miller affected C mu. So, which is 1 plus A V times C mu, and if you have significant amount of C mu, since the voltage gain it is high, for CE amplifier the input capacitance it was quite large. On the other hand, for common base amplifier, that C mu it is not having any contribution. So, we can say that if I compare common emitter and common base in terms of input capacitance, common base amplifier it is better. And as what will be the consequence of that? In case the upper cutoff frequency it is not only defined by the output node, if it is also defined by the input pole, namely if C in and R s they are defining the upper cutoff frequency, then we can see this advantage. So, in this example, since we are considering R s is equal to 0, that is why the effect of the C in is not coming in the frequency response. But if we consider in general, so the upper cutoff frequency defined by R s and C in, so that is the other candidate of the upper cutoff frequency, that may using this expression, and if we are having R s, it can be easily prominent that the common base circuit, since its input capacitance is low, it is useful for some high bandwidth application. So, now the next thing what we have to see, that even though we have seen that the voltage gain it is good, but input impedance is not so good. Now, if I compare again the C amplifier and C B, then and if I consider practical value of the source resistance, signal source resistance, because of the input impedance is low, we are expecting that primary input to emitter node there will be large attenuation. Namely, if I consider, say, this is the input signal V in having a finite value of the source resistance, followed by the input impedance of the amplifier. And since this R in is small, so we are expecting there will be big attenuation. So, in the next example, numerical example, what we will consider that R s, instead of considering 0 ohm, will take some practical value. Rest of the things we will keep as is, and then we can see what will be its consequence, particularly on the voltage gain. So, yes, so this is the this is what exactly what I was telling, that all the parameters here we are taking same except the source resistance. So, we are considering the source resistance, it is 10 kilo ohm. Now, let us see what will be the corresponding voltage gain. So, the voltage gain from this point to this point, namely emitter to collector, we already have seen that voltage gain it is G m into R o in parallel with R c. And then if I consider from this point to this point, primary input to the emitter node, it is having an attenuation, and that attenuation it is R in divided by R s plus R in. Now, this part we have calculated as 108.8, and then R in we obtained this R in, it is only 26 ohms, and then R s we are considering 10 k. So, R s plus R in it is 10026. So, that gives a big attenuation. So, the overall gain now with R s is equal to 10 k, it is quite small. I may let me, I think I did some calculation on that. Yes. So, this attenuation factor 108.85 getting multiplied by this attenuation factor, which is 0.0253. I think I am correct, and then that gives us the overall gain. It is only 2.758. No surprise, there is a huge attenuation from here to here of 0.025. So, the voltage gain, in summary, the voltage gain, it is very bad, particularly if I start considering practical value of the source impedance. Of course, it depends on the source impedance, but then even if you consider say 1 k, which may be in the many of the application, then also the this attenuation will be quite big. So, we need to be a little careful here. I guess correct here, 10 k. So, that is 26. Yeah, approximately you can see that this is 26 divided by 10 to the power 4. So, that gives us sorry, I will take it back. In fact, the attenuation, it is even more, and that is what I was wondering, that why the attenuation is only this much, and that gives us very low gain. In fact, the gain, it is less than 1. Okay. So, it is just 0.27. So, naturally, if we consider practical value of this source resistance, we can see the effect. In fact, if I consider R s, it is a lower, say R s is equal to 1 kilo ohm, then also this attenuation, it will be quite significant, and with this R s of 1 kilo ohm, the overall voltage gain, it is 2.758. Yeah, I think I have done this calculation for 1 k, and now if it is 10 k, the situation is really bad. Now, what is the effect on the output impedance on the other hand? Since we are considering the finite resistance R s, so let me use different color to explain that. Output resistance, if I see, it is having two components. One is R c and the resistance coming from the active part. So, the resistance coming from this active part, it is basically it is, you may recall, if I call this is R out dashed. So, that is the impedance of the active device. So, that is R pi in parallel with R s plus R o plus G m into R o into R pi in parallel with R s. And in this case, if I consider it is 10 k and R pi, it was 2.6 k. So, these two in parallel, again I think I do have the calculation. No, I do not have that, but whatever it is, this part it is 2.6 multiplied by 10 k. So, that is 10 divided by 12.6 k. So, that is 26 divided by 12.6. So, roughly we can say that this is 2 k. And now, if I consider R naught, which is you may recall this is 50 K, and this part it is quite big, and that is GM, which is 1 by 26, and then we do have 50 K, and then we do have roughly 2 K. Okay. So, let me use this space here. This part is really becoming clumsy here. So, what we are getting here, it is 100 2 into 50 100, and then we do have, this is kilo, this is also kilo, this is ohm. So, into 10 to the power 6 divided by 26. So, roughly we can say this part and this part close to 4, which means that 4 mega ohms. That is quite big, that is quite big. So, by having this source resistance, we may get an advantage that this resistance is quite large, but then overall resistance, output resistance, it is R C coming in parallel with R out and R out dash rather. So, though this R out dash it is quite large of say 4 mega ohms of magnitude. On the other hand, R C it is only 3 kilo ohms. So, we can say that it is having hardly any influence on the overall output resistance, because this 3 K it is quite small, it is, I should say, it is peanuts of the 4 mega ohm. So, the output resistance it is hardly getting affected by this R S, but we need to be careful that is mainly because this R C it is small. In case if we have an implementation where this R C it is quite large, then only we can see that output resistance of this entire circuit it is highly dependent on this R S. Okay, so this is the other example. Now, also the other thing probably we can do, we can observe that output input capacitance and upper cutoff frequency hardly it is in particularly input capacitance it is not getting changed, but then output I should not say output, the overall upper cutoff frequency it depends on the R S. So, let me clear this board and then again rewrite with different color. What we like to say that input capacitance C in it is C pi, and this is 10 picofarad, and then this R S and whatever the capacitance we do have here, the other end of this capacitance it is AC ground. So, we can say that from primary input to this point we do have one RC circuit defined by C in and this R S. So, one candidate of the upper cutoff frequency coming from this R S, let me call this is omega u dashed, is 1 by R S and C in, and this is 1 divided by 10 to the power 4, and C in it is 10 to the power. So, this is picofarad, 10 picofarad. So, this is minus 11. So, that gives us minus 7 here. So, this is equal to 10 to the power 7 radian per second. On the other hand, the upper cutoff frequency defined by the R out and C L, and let me denote this by omega u, which is equals to 1 by R out C L, and R out it is dominated by R C So, that is 3 kilo ohms, 3 into 10 to the power 3, and then we do have the 100 picofarad. So, that is 10 to the power minus 10. So, that gives us here again 10 to the power minus 7. So, in the numerator it becomes 10 to the power 7 divided by 3. So, yeah, so I should say 10 by 3 mega radian per second, and this is 10 mega radian per second. Now, incidentally, in this numerical example, still this is higher than this one. So, I should say omega u will define the overall upper cutoff frequency, but we need to be careful that R s if it is higher and higher, then this may also create the bandwidth limitation. So, the bottom line here it is, rather I should say the information other way, even though R s it is say 10 kilo ohm, since the input capacitance it is remaining low, unlike common emitter amplifier where the input capacitance it is large. Since this input capacitance for this circuit it is remaining low, this upper cutoff frequency it is still going beyond the other candidate of the upper cutoff frequency here. So, I should say the common base amplifier it is helping to design a relatively wide band amplifier. So, later we will see that how this information can be utilized. Now, similar kind of analysis can be done for the MOS counterpart, namely the common gate amplifier. Before we go into that, let me take a short break and then we will come back to analyze the common gate amplifier.